We've all seen those massive ships, right? Giant steel beasts hauling cargo across the ocean. Or those cruise ships floating cities packed with tourists. Ever wonder how they stay on course, maintain speed, or adjust to rough seas? That, my friend, is where control engineering comes in. Control engineering is all about automation. It's about designing systems that can operate without constant human intervention. Think of it like this. You set the thermostat in your house, and it automatically turns the heating or cooling on and off to keep the temperature just right. In the marine world, control engineering is crucial. Ships, submarines, even underwater robots rely on it for navigation, propulsion, ballast control, and more. It's what allows these complex machines to operate safely and efficiently. Now, the real workhorses of control engineering are feedback loops and PID controllers. Don't let the fancy names scare you, they're pretty straightforward once you break them down. Imagine you're steering a boat. You want to go straight ahead, but the wind and waves keep pushing you off course. So, what do? You constantly adjust the rudder, right? You look at where you're going, compare it to where you want to be, and make corrections. That, in a nutshell, is a feedback loop. It's a continuous cycle of measuring, comparing, and adjusting. In control engineering, feedback loops are used to keep systems on track. Let's say a ship wants to maintain a specific speed. A sensor measures the actual speed and sends that information to a controller. The controller compares the actual speed to the desired speed. If there's a difference, it sends a signal to the engine to adjust the power output. This cycle repeats constantly, ensuring the ship stays on target. Now let's talk about the brains of the operation, the PID controller. PID stands for Proportional Integral Derivative, but don't get bogged down in the technical terms. Think of it like a chef adjusting the heat under a pot of soup. The proportional part is like the chef's immediate reaction. If the soup is not hot enough, they turn up the heat. The more it needs to be heated, the more they turn it up. In a control system, this means the controller makes bigger adjustments when the error is larger. The integral part is like the chef keeping an eye on the overall temperature. If the soup is consistently too cold, they might need to increase the heat a bit more permanently. This ensures that even small, persistent errors are eventually eliminated. The derivative part is like the chef anticipating the future. If the soup is heating up too quickly, they lower the heat before it boils over. This helps prevent overshooting the target and causing instability. By combining these three actions, proportional, integral, and derivative, a PID controller can precisely regulate a system, keeping it stable and accurate. Real-world control from ships to submersibles. So where do we see these control systems in action? Everywhere in the marine world. Ships use them for autopilot systems, keeping them on course automatically. Dynamic positioning systems use feedback loops and PID controllers to keep ships stationary, even in strong currents or rough seas. Submarines rely on them for depth control, adjusting ballast tanks to ascend or descend precisely. Underwater robots use them for navigation and maneuvering, exploring the ocean depths with incredible accuracy. Think about remotely operated vehicles, those underwater drones used for everything from inspecting pipelines to exploring shipwrecks. They rely heavily on feedback loops and PID controllers to stay stable, move precisely, and manipulate objects underwater. Smooth sailing with automation. Key takeaways. Control engineering, with its trusty sidekicks, feedback loops, and PID controllers, is revolutionizing the marine industry. It's making ships safer, more efficient, and more autonomous. Just remember, it's all about maintaining balance and making adjustments based on real-time information. So the next time you see a massive ship cruising effortlessly across the ocean, think of the control systems working behind the scenes, keeping everything running smoothly. It's a testament to the power of engineering and the ingenuity of those who keep our seas humming.